Welcome to Science to Sleep By. Tonight, we'll take a calm journey into the story of something you know so well. Water. The very water you drink, the water in the oceans, the rain that falls from the sky, it all carries a history far older than our planet. In fact, the story of water begins before Earth was even formed. So, as you settle into bed, let your mind drift with me through the stars, across time, and into the deep history of water. A history older than Earth itself. When we look at the glass of water on a table, or when we hear the soft rhythm of waves breaking on a shore, we rarely stop to think about just how old that water truly is. We tend to see water as an ordinary, everyday part of our lives, a simple necessity that we use to drink, to bathe, to wash, and to nourish our world. Yet, the true story of water stretches unimaginably far back in time, into an era long before our planet Earth even came into existence. Water carries within it a history that is almost as old as the universe itself, and when we trace its journey, we discover that it was forged in the hearts of stars and scattered across the cosmos before ever finding its way to our blue planet. To begin, we have to step back in time, not millions of years, not even billions, but nearly 14 billion years ago, to the birth of the universe. At that moment, in the great expansion we call the Big Bang, the first ingredients of the cosmos were formed. The newborn universe was unimaginably hot and dense, filled with a blinding fireball of energy. Out of that storm of creation came the simplest elements, hydrogen and helium, the building blocks from which everything else in the universe would later emerge. Hydrogen, the lightest element, filled space in vast quantities. This was the first step in the long story of water, but hydrogen alone is not enough to make water. The second ingredient, oxygen, had not yet been born. For that, the universe had to wait until stars came into being. In the early cosmos, gravity gathered great clouds of hydrogen and helium together, squeezing them tighter and tighter until the immense pressure and heat at their cores triggered the first nuclear furnaces. These first stars lit up the darkness, burning brightly and furiously. Inside their cores, hydrogen atoms were fused into helium, and as these stars lived and died, heavier elements were slowly forged. It was within the fiery hearts of stars that oxygen atoms were created. A process that took millions upon millions of years. When the earliest generations of stars reached the ends of their lives, they exploded in violent supernova, scattering their newly made elements into space. Among those elements was oxygen. With hydrogen drifting freely through the cosmos and oxygen now scattered among the stars, the two had a chance to meet. And when hydrogen and oxygen combined in the cold reaches of interstellar space, the first molecules of water formed. Tiny crystals of ice clung to dust grains, hidden within great cosmic clouds, carried along by the winds of the galaxy. It is within these clouds of dust and gas that stars are born, and with them, planetary systems. That means that long before Earth was ever shaped, long before the sun ignited, water already existed, waiting in the darkness. This ancient water was not collected neatly in oceans, lakes, or rivers. Instead, it drifted silently in molecular clouds, often frozen onto particles of dust no larger than grains of sand. Telescopes today can detect these clouds, revealing that water vapor and ice are among the most abundant molecules in space. In fact, astronomers have found giant reservoirs of water in interstellar regions so vast that they contain more water than all the oceans of Earth combined, many trillions of times over. These findings remind us that water is not a rare substance, but a cosmic one, woven into the very fabric of galaxies. When we look at the hydrogen atoms in the water around us, we realize something remarkable. These atoms are ancient beyond comprehension. The hydrogen in every drop of water is as old as the universe itself. It has traveled across time and space for nearly 14 billion years, waiting to be part of the story of Earth. When you drink a sip of water, you are quite literally holding in your hand fragments of the oldest material in existence. The oxygen atoms, though younger than hydrogen, are still ancient, created billions of years ago in stars that lived and died long before the sun was born. This means that every glass of water we know today carries within it a blend of materials that are older than our planet, older even than our solar system. Consider the image of a massive star nearing the end of its life. It burns with such intensity that its outer layers swell and tremble. Deep within, nuclear reactions create heavier and heavier elements. In its final moments, the star collapses, then explodes, casting those elements into space. Among them are the precious oxygen atoms that will eventually combine with hydrogen to form water. In this sense, every molecule of water we know is a legacy of ancient stars. When we touch water, we are, in a very real way, touching stardust that has been transformed and recycled through the cosmos. As time moved forward, billions of years passed before Earth was formed. During that span, water continued drifting through interstellar clouds, settling on icy bodies such as comets and asteroids, which became the carriers of water across the universe. These wandering objects preserved the ancient molecules, protecting them from destruction, until they could be delivered to young planets like ours. But even before delivery, water's presence had already influenced the birthplaces of stars and planets, shaping the very environments where new systems would arise. To imagine this long prelude to Earth is to place ourselves in a perspective that is both humbling and awe-inspiring. The water we know today did not suddenly appear with Earth. It is not an invention of our planet. Instead, it is part of an ancient cosmic inheritance, assembled from the simplest building blocks of the universe, carried through time by stars and space, until at last it became part of Earth's story. Hydrogen, born in the Big Bang, oxygen, forged in stars. Together, they created a molecule that would one day cradle life itself. This ancient history invites us to look at water in a new way. Instead of seeing it as ordinary, we see it as extraordinary. Instead of thinking of it as temporary, we realize it is timeless. Long before oceans filled Earth's surface, long before rivers carved valleys or rain nourished forests, water was already present, older than the rocks beneath our feet, older than the soil, older even than the blue sky. In its very essence, water tells us that our world is connected to the stars, and that something as simple as a glass of water is a direct link to the deep history of the universe. This is the story of the ancient origins of water, a story that begins not on Earth, but in the stars, where the ingredients for life itself were born. Hydrogen drifting endlessly through space, oxygen created in the final breaths of massive stars, the two coming together in cosmic clouds, forming the molecules that would eventually find their way to planets like ours. This story reminds us that water's journey is far greater than the life it sustains today, that it has been present since the earliest times, patiently waiting through the ages, until at last it became part of the oceans, the rain, and the streams of Earth, carrying with it the memory of a history older than Earth itself. When we gaze up at the night sky, we often imagine the vast emptiness of space, a cold void sprinkled with distant stars. But space is not truly empty. Between those stars lie enormous clouds of gas and dust, stretching across light years, forming cradles where new stars are born. Hidden within these clouds is something familiar, something we know intimately here on Earth: water. Yet in space, water does not flow in rivers or gather in oceans. Instead, it exists as tiny frozen crystals, thin films on dust grains, or as vapor drifting through interstellar clouds. It waits quietly, scattered across the galaxy, playing a subtle yet powerful role in shaping the universe we see today. To understand how water came to exist in interstellar space, we need to imagine these giant molecular clouds, vast regions where temperatures drop to just a few degrees above absolute zero. At these extreme cold levels, atoms and molecules slow down, allowing them to stick together. Dust grains, made of silicates and carbon, float inside these clouds. They serve as microscopic platforms where chemical reactions can occur. When a hydrogen atom meets an oxygen atom on the surface of one of these dust grains, they bond, forming a molecule of water. Over time, countless molecules of water collect, freezing into icy coatings that wrap around the grains. In this way, entire clouds of dust and gas become saturated with water ice. This water is ancient. It formed long before Earth, long before our solar system. The same molecules that now lie frozen in interstellar space have been traveling for billions of years, carried along as stars are born and destroyed. Astronomers using powerful telescopes, such as those that observe in the infrared spectrum, have detected the spectral fingerprints of water in these regions. What they see is astonishing. Water is one of the most common molecules in the universe. It is not a rare exception, but a widespread feature of the cosmos, existing wherever hydrogen and oxygen can meet under the right conditions. When we hear of water in space, it can be difficult to imagine. On Earth, water feels familiar. It pours from taps, fills lakes, and falls as rain. But in interstellar space, water takes on alien forms. Some of it exists as vapor, floating invisibly in cold clouds. Some of it is frozen into hard, crystalline ice on tiny dust grains, forming mantles that coat particles only a fraction of the width of a human hair. These ice-coated grains can clump together, slowly forming larger structures that eventually become comets, asteroids, or even parts of forming planets. In this sense, water in interstellar space is more than a passive ingredient. It is a participant in the grand process of building new worlds. Telescopes have revealed astonishing reservoirs of water in space. For example, astronomers have discovered a cloud of water vapor surrounding a distant black hole that contains an amount of water hundreds of thousands of times greater than all the oceans on Earth combined. This immense reservoir, swirling in the distant reaches of the cosmos, reminds us that water is not a substance confined to our planet. It is a universal material, scattered generously throughout galaxies, drifting in interstellar clouds, and clinging to the dust that will one day form stars and planets. In the Orion Nebula, a region of active star formation just over 1,000 light-years away, astronomers have detected rich signatures of water vapor. There, young stars are forming from collapsing clouds of gas, and around them, disks of dust and ice are taking shape. Within those disks, water molecules help cool the material, allowing it to collapse further, guiding the process of star and planet formation. Without water in interstellar space, the birth of stars and planets might proceed differently, perhaps even less efficiently. Water, therefore, plays a quiet but essential role in the architecture of the universe. The water we find in interstellar space also carries clues about the chemistry of the cosmos. By studying its composition, astronomers can learn how molecules form, how they survive the harsh radiation of space, and how they contribute to the early stages of planetary systems. In many cases, the water found in interstellar clouds has a chemical fingerprint similar to the water on Earth. This suggests that some of the water on our planet may have been preserved from these ancient interstellar sources, surviving the violent birth of the solar system to eventually become part of our oceans. To think of water drifting between the stars is to think of a connection that links our planet to the wider galaxy. Each droplet we see today may have once been part of an interstellar cloud, frozen onto dust, waiting to be drawn into the formation of a new system. The same molecules that sparkle as frost on interstellar grains may one day flow as liquid water on the surface of a distant world. This continuity across time and space reminds us that water is not simply an earthly feature, but a universal thread, stitching together the stories of stars, planets, and life. Imagine a region of space where new stars are beginning to ignite. Around them, disks of gas and dust swirl, glowing faintly. Within those disks, water ice clings to particles, helping them stick together. Over time, these particles collide and merge, forming pebbles, then rocks, then larger bodies that may become planets. Water, locked inside these early building blocks, is carried into new worlds. Some of it remains frozen deep within, while some is delivered later by comets or asteroids. In this way, the water that once floated silently in interstellar space finds its way into the seas and rivers of planets, like Earth. Even beyond our own galaxy, astronomers have detected water in the atmospheres of exoplanet planets orbiting distant stars. These discoveries are possible because water leaves a clear fingerprint in light, absorbing and emitting radiation in specific wavelengths. By studying these signatures, scientists can confirm that water is not confined to our solar system, but is widespread throughout the universe. This reinforces the idea that water is a fundamental feature of the cosmos, and where water exists, the potential for life may also exist. But water in interstellar space is not just about chemistry or planet formation. It also holds a certain poetic quality. To know that the same water molecules drifting between stars may someday flow through rivers on a distant world connects us deeply to the cosmos. It suggests that the universe itself is full of continuity, that the cycles we see on Earth, the rain falling, the rivers flowing, the oceans rising and evaporating, are part of a much larger cycle that spans light years. Water is not just local, it is cosmic. The interstellar presence of water also challenges us to think about origins. When you hold a glass of water, it is not just something that has been on Earth for billions of years. Its molecules were once drifting in the cold, dark spaces between stars. They were frozen onto dust grains, carried through nebulae, and preserved across epochs before eventually becoming part of our world. That connection links us directly to interstellar clouds, to the birthplaces of stars, and to the ancient history of the universe. In the stillness of interstellar space, water waits. It gathers on dust, it floats as vapor, it travels through galaxies. It plays a role in cooling the clouds that form stars. It becomes part of the disks that form planets. And eventually, it finds its way to places where it can flow, shaping landscapes, and perhaps even nurturing life. It is a quiet traveler, timeless and patient, carrying within it a story that stretches across the stars, a story that began long before Earth and continues still today. In the water-rich clouds that drift silently through the galaxy, understand how Earth came to hold its vast oceans and the countless rivers, lakes, and streams that define its surface. We must travel back to the earliest chapters of our planet's history. Earth did not begin as a water-rich world. In its infancy, more than 4.5 billion years ago, our planet was a molten sphere, seared by constant impacts, with surface temperatures so high that any liquid water would have instantly boiled away into space. For a long time, Earth was an inhospitable landscape of fire and stone, and yet today, it is a world draped in blue, covered in water that nurtures life. The key to this transformation lies in the icy wanderers of the cosmos, comets and asteroids, which served as delivery vessels for one of the most precious substances in the universe. Comets are among the most ancient and mysterious objects in the solar system. They are often described as dirty snowballs, mixtures of ice, dust, and rock that formed in the frigid outskirts of the solar system. Far from the heat of the sun, comets preserved water in frozen form, locked away for billions of years. When these icy bodies are disturbed by the gravitational tug of giant planets or collisions with one another, they can be sent on long journeys inward, toward the sun. As they approach, their icy surfaces warm, releasing gas and dust into magnificent tails that stretch across space. To the human eye, comets appear as beautiful streaks of light, but their true significance lies in what they carry: ancient water, preserved since the earliest days of the solar system. Asteroids, by contrast, are rocky remnants of planet formation. While many are dry, some contain significant amounts of water locked within minerals. These hydrated asteroids, particularly those from the outer regions of the asteroid belt, acted as couriers of water, crashing into Earth and releasing their cargo into the young planet's surface. Unlike comets, which are rich in volatile ices, these asteroids delivered water more gradually, through the release of chemically bound molecules that were incorporated into Earth's crust and mantle. The story of how these objects delivered water to Earth is written in both cosmic violence and cosmic generosity. In the early solar system, collisions were frequent and catastrophic. Young planets and planetesimals were bombarded relentlessly by comets and asteroids in a period known as the Late Heavy Bombardment, roughly 4 billion years ago. During this era, icy bodies from the outer solar system, and hydrated asteroids from the asteroid belt rained down upon Earth. Each impact released energy, sometimes enough to melt rock and reshape landscapes. But alongside that destruction came the gift of water. Slowly, over millions of years, these deliveries built up reservoirs of liquid, seeding Earth with the oceans that would one day become the cradle of life. Scientists have traced this story by studying the chemical signatures of water on Earth and comparing them to water found in comets and asteroids. One of the most important clues comes from the ratio of deuterium to hydrogen in water molecules. Deuterium is a heavier form of hydrogen, and the relative abundance of deuterium can act like a fingerprint, identifying the origin of water. By measuring these ratios in different celestial bodies, astronomers can determine whether Earth's water more closely resembles that from comets or asteroids. Surprisingly, many comets studied so far have deuterium ratios that do not match Earth's oceans. Instead, the water locked in certain asteroids, particularly carbonaceous chondrites, matches Earth's water almost perfectly. This evidence suggests that while comets may have contributed, asteroids were likely the primary couriers of water to Earth. Yet the story is not entirely one-sided. Comets, with their spectacular tails and icy cores, may still have played an important role. Even if they did not supply the majority of Earth's water, they certainly delivered some, and perhaps more importantly, they carried other vital ingredients. Alongside water, comets harbor organic molecules, the carbon-based compounds that are the building blocks of life. When comets slammed into the young Earth, they may have enriched it not only with water, but also with the chemical seeds necessary for biology to emerge. In this sense, comets can be thought of as messengers, bringing both water and the spark of life from the cold edges of the solar system to a young, fiery world. The delivery of water was not a simple one-time event. It was a prolonged process, occurring over hundreds of millions of years. Earth's early atmosphere and geology made it difficult for water to accumulate at first. Volcanic eruptions spewed gases into the sky, creating a toxic, heavy atmosphere. The planet's crust shifted and cracked, allowing heat to escape. But as water continued to arrive from impacts, and as Earth slowly cooled, it began to settle into basins, forming the first primitive oceans. Those early seas were likely shallow and scattered, but over time, they deepened and expanded, until at last Earth became a water world, a planet where blue oceans dominated the surface. The evidence of this cosmic delivery is preserved not only in Earth's water, but also in its geological history. Ancient rocks, some more than 3 billion years old, contain signatures of water trapped during their formation. These rocks tell us that Earth had liquid water relatively early in its history, suggesting that delivery by comets and asteroids happened swiftly after the planet's formation. In other words, Earth's transformation into a watery world occurred quickly on cosmic timescales, laying the foundation for life to emerge in the planet's early chapters. What makes this story even more fascinating is that Earth was not the only recipient of such deliveries. Mars, too, shows evidence of having once hosted vast amounts of water. Ancient river valleys, dried lakebeds, and mineral deposits tell us that Mars was once a world of flowing water. Like Earth, it likely received its water from impacts by asteroids and comets. Even today, icy comets continue to pass through the solar system, some crossing paths with planets, carrying with them the same cargo they have carried for billions of years. These bodies act as time capsules, preserving not only water, but also the conditions of the early solar system, allowing scientists to peer back into the past. When we think about comets and asteroids as deliverers of water, we also realize they may be delivering potential for life elsewhere. In distant planetary systems, icy comets and rocky asteroids likely play similar roles, bombarding young planets with water and organics. This raises a profound question. If Earth's oceans were born from cosmic deliveries, could other worlds also become water-rich and habitable through the same process? The presence of water on exoplanet, detected in recent years, suggests that this may be a universal pattern, one repeated throughout the galaxy. The poetic nature of this story lies in its mixture of violence and gentleness. Comets and asteroids arrive as destructive forces, crashing into planets with immense energy, reshaping landscapes and leaving scars that last for billions of years. Yet in their destruction, they also bring life-giving water, the very substance that allows planets like Earth to become havens of biology. This paradox that cosmic chaos could create the conditions for peace and life reminds us that water's journey is not simple but filled with contrasts. To hold a glass of water today is to hold the memory of this ancient process. The molecules within it may have traveled through interstellar space, frozen on dust grains incorporated into a comet, and hurled across light years before finally colliding with Earth. They may have survived the violent impact of an asteroid, becoming part of the early oceans that spread across the surface of the planet. Every drop of water carries within it the story of cosmic delivery, a story of icy wanderers from the outer solar system bringing the essential ingredient of life to a once dry world. This is the legacy of comets and asteroids, carriers of water, couriers of organic molecules, architects of oceans, and perhaps, in their own way, midwives of life itself. Their journeys remind us that water did not originate on Earth, but was brought here through countless deliveries, each one a small but essential contribution to the blue planet we now call home. When we picture our planet from space, we see a world cloaked in shimmering blue, its oceans stretching across vast continents, reflecting the light of the sun. This image has become so iconic that Earth is often called the blue planet. But what is easy to forget is that Earth did not begin this way. In its infancy, it was not a world covered in water, but rather a fiery sphere, scarred by impacts and molten across its surface. The oceans that now define Earth's appearance and sustain its life had to be born, and that birth was a slow, dramatic, and deeply cosmic story that unfolded across hundreds of millions of years. To understand how Earth's oceans came to be, we must return to a time more than 4.5 billion years ago, when the young solar system was a chaotic place. Our planet had just formed from a swirling disk of gas and dust, a protoplanet that grew larger as it swept up material from its orbit. But in those early years, Earth was anything but stable. It was struck repeatedly by asteroids, comets, and other debris left over from the formation of the solar system. These impacts released extraordinary amounts of energy, heating the surface to the point of melting. The Earth of that time was a world dominated by magma, a fiery and unstable place where no liquid water could exist. And yet, hidden within this chaos, the ingredients for oceans were already being assembled. Some of the water was delivered by icy bodies from space, carried by asteroids and comets, each impact depositing more water into the growing reservoirs of Earth. But another source of water was locked deep within the planet itself. As Earth formed, it incorporated water molecules trapped inside minerals, bound within the very structure of the rocks. As the planet's interior heated up, this water was gradually released through volcanic eruptions, escaping into the atmosphere as vapor. Over millions of years, the steady outgassing of volcanoes filled the skies with steam, carbon dioxide, methane, and other gases, creating a dense and heavy atmosphere around the young Earth. At first, this atmosphere was far too hot for liquid water to exist. Steam rose and lingered in the air, unable to condense. The surface below was molten, glowing with the heat of impacts and radioactive decay. But as time passed, Earth began to cool. The frequency of catastrophic impacts declined. The molten surface began to harden into a solid crust. Slowly, the conditions became favorable for a great transformation. As temperatures dropped, the steam in the atmosphere began to condense into raindrops. At first, the rain may have evaporated as soon as it touched the ground, sizzled away by the lingering heat. But over time, the cooling continued, and the rains became steady. The skies darkened with endless storms, and the young Earth was drenched in rainfall unlike anything we could imagine today. This rain fell not for days, not for weeks, but for thousands and thousands of years. Torrents of water poured down from the skies, filling the basins and depressions in Earth's crust. Slowly, Puddles grew into lakes, lakes merged into seas, and seas expanded into vast oceans. These were the first true oceans of Earth, and their formation marked one of the most significant turning points in the history of the planet. No longer was Earth simply a rocky body orbiting the sun. It was now a water world, with oceans that shimmered under the sky, setting the stage for everything that would follow. The birth of Earth's oceans was not a gentle process. The same volcanic eruptions that had filled the air with steam continued to shape the landscape, creating islands, ridges, and basins that defined the boundaries of the seas. Water interacted with the rocks, dissolving minerals and carrying them into the oceans, changing their chemistry. Lightning flashed in the storm-filled skies, striking the surface of the oceans, adding energy to the mix. These interactions created a dynamic environment, one in which the basic ingredients of life could eventually take root. Scientists today study the oldest rocks on Earth to understand when liquid water first appeared. Some of these rocks, more than 4 billion years old, contain isotopic signatures that reveal they were formed in the presence of water. This means that oceans existed on Earth astonishingly early in its history, perhaps within only a few 100 million years after the planet itself was born. Such evidence suggests that the process of ocean formation was swift and relentless, a natural consequence of Earth's cooling, its volcanic outgassing, and the bombardment of icy bodies from space. The scale of these early oceans is difficult to imagine. Today, Earth's oceans cover more than 70% of the surface, containing nearly all of the planet's water. Yet in the beginning, they may have looked very different. Some theories suggest that the first oceans were shallower, scattered across a still-forming crust that shifted and cracked under the weight of volcanic activity. Others propose that Earth's oceans were already vast and deep, filling basins that extended across the surface. What is certain is that water, once unleashed, quickly became one of the dominant features of the planet. The birth of the oceans also altered Earth's climate in profound ways. Water is a stabilizer. It absorbs heat, moderates temperatures, and creates cycles of evaporation and condensation that balance the atmosphere. As the first oceans spread, they began to cool the planet further, creating a more stable environment. Clouds formed, rains continued, and the cycle of water evaporation from the surface, condensation in the air, rainfall back to the ground was established. This water cycle, which continues today, has its origins in those ancient times, when the first great rains filled the basins of the earth. We can also imagine how alien those early oceans must have seemed. Without continents shaped by plate tectonics, the geography of Earth was entirely different. Land masses were smaller, volcanic islands rising from a sea that dominated the horizon. The waters themselves may have been murky, rich with dissolved minerals, chemicals, and particles carried from the crust. The air above was thick with volcanic gases, creating skies that were likely red, orange, or hazy with dust. Yet, in this seemingly hostile environment, the oceans were quietly preparing for the greatest event of all, the emergence of life. The formation of Earth's oceans was more than just a geological event. It was the foundation upon which biology itself would rest. Without oceans, Earth would have remained a barren, rocky planet, with no place for life to take hold. But with oceans, the planet gained a vast, stable environment where molecules could interact, combine, and evolve. The oceans became laboratories of chemistry, stirred by heat from the Earth's interior and energy from the sun above. They became the cradle in which the first cells would eventually form, billions of years later. To think of the birth of Earth's oceans is to think of the transformation of a world. From a fiery sphere of rock and lava, Earth became a planet of water. From skies filled with steam and fire, it became a planet of rain and storms. From barren surfaces, it became a planet with seas that stretched toward the horizon. This transformation did not happen overnight, but across countless years, shaped by the forces of geology, astronomy, and chemistry. Yet once it was complete, Earth was forever changed. It was no longer just another rocky planet orbiting a star. It was a water world, unique in its richness, set apart by its oceans, that would one day give rise to life. Every wave we see today, Every drop of water in our oceans carries within it the memory of that birth. The rain that falls from the sky is part of a cycle that began billions of years ago, when the first steam condensed and fell to the ground. The oceans that cover our world are the direct descendants of those first, ancient seas. To look upon the waters of Earth is to see not just a present reality, but the result of an ancient story, one that began with fire, chaos, and storm, and ended with the birth of oceans that would define our planet for the rest of its history. Waiter, as a cosmic connector. When we think about water on Earth, it is easy to see it as something local, something tied only to our own planet. It flows in our rivers, it gathers in our lakes, it stretches across our oceans, and it falls as rain from the skies. But to understand water only in this narrow sense is to miss the larger truth. Water is not just earthly, it is cosmic. It exists throughout the universe, from interstellar clouds to distant planets, from icy moons to vapor-filled atmospheres light years away. In this way, water becomes more than a substance, it becomes a connector, linking our world to the stars, linking our existence to the vast and ancient processes of the cosmos. To see water in this light is to see that every drop we encounter on Earth is part of a greater whole, a molecule with a story that stretches across space and time. The idea of water as a cosmic connector begins with its origins. Hydrogen, born in the first moments of the universe, and oxygen, forged in the fiery hearts of stars, combined billions of years ago to form the earliest molecules of water. These molecules drifted through the cold regions of interstellar space, attaching to dust grains, freezing into icy mantles, or condensing into vapor that lingered in molecular clouds. These clouds were the birthplaces of stars and planets, and within them, water served not only as a byproduct, but as a vital ingredient in shaping the environments from which new worlds emerged. This simple molecule, HO, created bridges between the earliest stars and the youngest planets, ensuring that water was present from the very start of planetary formation. When Earth was born, it inherited its water from both interstellar origins and cosmic deliveries. But Earth is not unique in this inheritance. Mars, too, once had water, with ancient rivers and lakes carving its red surface. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, harbor vast oceans beneath their frozen crusts, oceans that are still liquid today, warmed by the tidal forces of their giant parent planets. Even far beyond our solar system, astronomers have detected the presence of water vapor in the atmospheres of exoplanets. Some of these worlds are giant gas planets, scorching hot and hostile, yet carrying signatures of water in their skies. Others are smaller, rocky planets orbiting in what we call the habitable zone, the region around a star where liquid water could exist. These discoveries tell us that water is not isolated to Earth. It is woven into the universe itself, appearing again and again in environments near and far. This repetition is what makes water such a powerful connector. When we study the oceans on Earth, we are not only studying our own planet, we are studying a phenomenon that exists across the cosmos. When we explore icy moons, drilling into the ice or flying spacecraft through geysers that erupt from their surfaces, we are connecting our search for water with the search for life. The same chemical properties that make water so vital on Earth, the way it dissolves nutrients, transports heat, and provides a stable medium for chemical reactions, make it equally vital elsewhere. In this way, water becomes the common thread that unites our search for habitable worlds, the bridge that links biology on Earth to the possibility of biology elsewhere. Consider Europa, a moon orbiting Jupiter. Its surface is a shell of ice, cracked and streaked with ridges, evidence of a dynamic and shifting exterior. Beneath this shell, scientists are confident that a global ocean lies hidden, kept liquid by the gravitational tug of Jupiter, which flexes and warms the moon's interior. That ocean may be twice as large as all the oceans on Earth combined. Enceladus, a smaller moon of Saturn, offers another astonishing connection. From its icy surface, plumes of water erupt into space, carrying not only water, but also organic molecules and salts. Spacecraft flying through these plumes have detected these ingredients directly. offering tantalizing evidence that conditions beneath the surface could resemble those that nurtured life on Earth. In both cases, the presence of water links these distant moons to our own story. Though separated by hundreds of millions of miles, their oceans are part of the same cosmic cycle, formed from the same processes that delivered water to Earth. When we imagine the possibility of life in these distant seas, we are reminded that water may be the great unifier, the element that connects life wherever it exists. The oceans beneath the ice of Europa or Enceladus may not be so different from the oceans that once sheltered Earth's earliest life forms billions of years ago. Beyond our solar system, the connection becomes even grander. Astronomers using powerful instruments like the Hubble Space Telescope and the James Webb Space Telescope have detected the spectral fingerprints of water in the atmospheres of exoplanets. These discoveries show us that water is not confined to our corner of the galaxy, but is widespread, appearing in systems light years away. Some of these planets orbit stars very different from our Sun, yet they still carry traces of water vapor. This demonstrates that water is not a rare anomaly, but a recurring outcome of the laws of physics and chemistry. Where hydrogen and oxygen exist under the right conditions, water forms naturally, and wherever it forms, it may create opportunities for life. This cosmic presence of water also shapes our philosophical view of existence. On Earth, water is the foundation of all biology. It flows through our bodies, makes up most of our cells, and drives every ecological system we know. To learn that water is common across the universe is to imagine that life too may be common. Water becomes the connector not only between planets and stars, but between civilizations, between possible life forms separated by light years, between us and the unknown. It transforms our sense of isolation into a sense of connection, a recognition that we are part of a larger story written in the molecules of the cosmos. Even here on Earth, water reminds us of its cosmic heritage. The hydrogen atoms in each molecule are nearly as old as the universe itself, created in the first minutes after the Big Bang. The oxygen atoms were forged in stars that lived and died long before the sun was born. When those atoms combined to form water, they became part of a cosmic lineage that stretches back billions of years. To drink water, to swim in it, to feel rain on our skin, is to interact directly with the ancient fabric of the universe. This simple act links us to the stars, reminding us that our daily lives are interwoven with processes that extend across galaxies. Water's role as a connector also extends into the future. As humans look toward exploration beyond Earth, water becomes a vital resource. On the moon, ice-hidden and shadowed craters may one day support human settlements. On Mars, deposits of subsurface ice could provide drinking water and fuel for rockets. The search for water is the search for possibility, for survival, for expansion. It connects our dreams of exploration with the practical necessities of life. Every mission that scans the skies for signs of water is part of this ongoing thread, tying our survival to the same molecule that ties us to the cosmos. The story of water as a cosmic connector is not only scientific, but deeply poetic. It tells us that what we see around us is not isolated, but part of something vast and universal. The rivers that carve valleys on Earth echo the channels that once flowed on Mars. The oceans that cradle our continents mirror the hidden seas of distant moons. The clouds that gather above us are kin to the vapor drifting in interstellar space. Every drop, every molecule is part of a grand continuum that stretches across time and distance. To reflect on water in this way is to see that it is more than a resource or a necessity. It is a bridge, connecting us to the past, to the stars, to other worlds, and perhaps even to other forms of life. It is the thread that ties Earth to the cosmos, reminding us that we are not separate but connected, not isolated but part of a greater whole. Water, in its simplicity, is the universal language of the universe, the molecule that whispers of unity, continuity, and connection across the vastness of space. Life, in all its vast diversity and mystery, traces its origins back to the presence of water. On Earth, every living thing is bound to water, not merely as a backdrop to existence, but as the very stage upon which the play of biology unfolds. To understand why life exists here, to understand how simple molecules grew into complex organisms, and to understand why we search for life beyond our planet, we must turn to water. It is not simply a supporting character in life's story, it is the heart of it, the essential ingredient that made life possible in the first place. Water is not unique in the universe in its elemental composition. Hydrogen is the most abundant element in existence, forged in the earliest moments after the Big Bang. Oxygen, though less common, is still one of the most plentiful elements, created in the fiery furnaces of dying stars. Yet it is when these two elements bond to form water that something remarkable happens. Water gains a set of physical and chemical properties unlike those of most other substances. It can dissolve a wide array of compounds, making it an ideal medium for complex chemistry. It has a high heat capacity, allowing it to stabilize environments against dramatic temperature shifts. It expands when it freezes, ensuring that ice floats and oceans do not freeze from the bottom up. These properties may seem simple, but they created a world where life could not just emerge, but also thrive. On early Earth, water gathered into vast oceans that covered most of the surface. These oceans were not just passive bodies of liquid, they were laboratories on a planetary scale. In these waters, simple molecules like carbon dioxide, methane, ammonia, and nitrogen dissolve and mingle. Lightning storms, volcanic eruptions, and the sun's ultraviolet rays added energy to this mixture, sparking reactions that began forming organic compounds, amino acids, lipids, and nucleotides. These are the building blocks of life, the alphabet of biology. And it was water that provided the solvent in which these letters first align. Without water to host these chemical dances, the pathways to life would have been limited, stunted, or perhaps impossible altogether. One of the most striking features of water is its ability to act as a solvent. Chemists often call it the universal solvent because it can dissolve more substances than any other liquid. This makes it uniquely suited to supporting life, since living systems require constant chemical reactions. Inside a single cell, thousands of reactions take place at any given moment, all mediated by water. It dissolves salts, sugars, proteins, and gases, allowing them to move freely, collide, and interact. It carries nutrients in and waste out. In essence, water is the medium that makes metabolism possible. Without it, cells would be static, lifeless structures. With it, they become dynamic, living systems, capable of growth, adaptation, and evolution. In the early oceans, water also played a protective role. The sun's young light was harsh, its ultraviolet rays capable of breaking apart fragile molecules. Yet water absorbed and scattered much of this energy, creating a shield that allowed delicate organic compounds to persist long enough to interact and evolve. At the same time, hydrothermal vents on the ocean floor may have provided the conditions necessary for life's spark. These vents released mineral-rich fluids into the sea, offering not only energy but also natural scaffolds for chemical reactions. In these environments, water once again was central, carrying minerals, dissolving compounds, and creating gradients of temperature and chemistry that may have allowed the first protocells to form. Protocells, primitive structures made of lipids that formed tiny bubbles in water, represent one of the great steps toward life. These bubbles, simple though they were, could trap organic molecules inside, concentrating them and allowing reactions to occur more efficiently. It is no coincidence that these structures formed in water. Lipids naturally align themselves in aqueous environments, forming membranes that separate inside from outside. This property laid the groundwork for the first cells. From this beginning, evolution could take hold, and biology as we know it began its slow, patient unfolding. Even after life began, water remained central. Photosynthesis, the process by which plants, algae, and cyanobacteria convert sunlight into energy, depends directly on water. The splitting of water molecules releases the oxygen that fills our atmosphere, making aerobic life, including humans, possible. Cellular respiration, the process by which organisms convert nutrients into usable energy, also takes place in water-rich environments within cells. The cycle of water on Earth, the constant evaporation, condensation, and precipitation ensures that ecosystems remain balanced, carrying nutrients, shaping climates, and enabling migration and adaptation. Water is not just where life began, it is where life continues to exist, a continuous thread from the first protocells to modern complexity. When scientists search for life beyond Earth, the presence of water is their guiding principle. Follow the water has become the mantra of astrobiology. Mars, once rich in rivers, lakes, and possibly oceans, is studied with relentless detail because its watery past suggests it might have harbored life. Europa and Enceladus, moons with oceans beneath their icy shells, are prime targets for future missions because they combine water with heat and organic chemistry, ingredients essential for biology. Even distant exoplanets are studied for signs of water vapor in their atmospheres, as this could be the first clue that they have conditions suitable for life. The role of water in life's spark on Earth makes it reasonable to believe that wherever water exists, the potential for life might exist as well. What makes this idea even more profound is the realization that the water on Earth is older than Earth itself. The molecules in our oceans may have formed in interstellar clouds long before the solar system was born. Some of it was delivered by comets and asteroids, carrying water across billions of miles of space. This means that the same water molecules that once floated in the cold darkness between stars eventually filled the oceans where life began. To say that life began in water is also to say that life began in something timeless, something that connects us directly to the stars. Every cell in our body is filled with water, and that water is part of a story older than our planet. Water's role in life's spark is not just about chemistry or physics. It is about continuity. It is about how a simple molecule became the foundation for something as complex and varied as the biosphere of Earth. It is about how hydrogen and oxygen, born in stars, became the rivers and oceans that nurtured the first living things. It is about how the same molecule sustains us today, carrying within it the memory of its cosmic journey. To drink water is to take part in this story, to connect with the origins of life and the processes that made it possible. In reflecting on water's role, one begins to see that life is not separate from the universe, but an expression of it. Water allowed atoms to assemble into molecules, molecules into cells, and cells into organisms. It allowed chemistry to become biology, biology to become consciousness, and consciousness to reflect upon itself. This chain of events, so improbable, yet so inevitable, given water's properties, reminds us that the spark of life is not an isolated accident, but part of a larger pattern written into the universe itself. Water is both the medium and the message, the element that holds together the fragile and wondrous thing we call life. When we lift a glass of water to our lips, when we hear the gentle rush of a river, or see the vastness of the ocean, it feels like something ordinary, a daily and familiar presence. Yet hidden in every drop is a story so ancient and so far-reaching that it transforms this simple act into something extraordinary. The molecules of water that flow through our bodies and our planet have a lineage that predates Earth itself. They were forged in cosmic events long before our sun was born, shaped by processes that unfolded in the hearts of stars and the cold reaches of interstellar space. This realization reveals a truth both humbling and profound. We share a cosmic heritage. The water that sustains our lives is not simply of Earth, it is of the universe, connecting us to galaxies, to stars, and to worlds that may lie unimaginably far away. To see water as part of a shared cosmic heritage, we must first understand its origins. Hydrogen, one of the two elements that make up water, was born in the very beginning, in the first minutes after the Big Bang. In that fiery birth of the universe, protons and electrons combined to form the simplest atom, and from that atom, the universe began its long expansion. For hundreds of millions of years, hydrogen filled the cosmos, gathering into clouds that would eventually collapse under their own gravity, igniting to form the first stars. Oxygen, by contrast, is much younger. It could not form in the chaos of the early universe. Instead, it was born within the furnaces of stars. Through nuclear fusion, stars took lighter elements and forged them into heavier ones, creating oxygen alongside carbon, nitrogen, and many other building blocks of life. When those stars reached the end of their lives, they scattered oxygen into space through supernova explosions, seeding the cosmos with the raw ingredients that would one day make water. Hydrogen and oxygen met again in the cold, dark regions of interstellar clouds. Here in the shadows of space, these atoms combined on the surfaces of dust grains, forming molecules of water ice. These icy particles collected, drifted, and froze, becoming part of the vast clouds from which new stars and planets would emerge. In this way, the water that exists on Earth today had already taken shape long before our planet was born. Some of it may have been preserved in icy reservoirs at the edges of the young solar system, waiting to be delivered to Earth by comets and asteroids. Some of it may have condensed directly as the planet formed, trapped in the rocks and minerals of its crust. However, it arrived. Its origins stretch back billions of years, connecting Earth's oceans to the very processes that shape the universe itself. This cosmic history makes every encounter with water an encounter with something ancient. The hydrogen atoms in a sip of water are nearly 14 billion years old, created in the earliest moments of existence. The oxygen atoms are younger, perhaps 5 to 7 billion years old, born in stars that lived and died before the sun. When these atoms combined to form water molecules, they became part of a story that spans time and distance. To drink water is to drink the memory of stars, to take into ourselves the very matter that once blazed in distant galaxies. This is the essence of a shared cosmic heritage. We are not separate from the universe, but participants in its unfolding, made possible by the same molecules that traverse space and time. On Earth, water became the medium for life, but its story does not stop here. Across the solar system, we see signs of this same molecule. Mars bears evidence of ancient rivers and lakes, its surface carved by the flow of water long ago. The icy moons of Jupiter and Saturn, Europa, Ganymede, and Enceladus harbor subsurface oceans, vast reserves of liquid water hidden beneath layers of ice. Even tiny comets, hurtling through the outer reaches of our solar system, carry water frozen within them, remnants of the earliest days of planetary formation. Each of these worlds holds water that is fundamentally the same as ours, forged from the same cosmic origins. In this sense, the oceans of Europa are kin to the oceans of Earth. The frozen ice of a comet shares its ancestry with the rain that falls upon our fields. The water molecules are siblings, scattered across space, yet bound by a shared beginning. When astronomers look beyond our solar system, the story deepens further. In distant exoplanet-orbiting stars light years away, the spectral signatures of water have been detected. Water vapor drifts in the atmospheres of alien worlds, proof that this molecule is not confined to our tiny corner of the cosmos. It is woven into the very fabric of planetary systems across the galaxy. This means that the heritage of water is not just shared between Earth and its neighbors, but may extend across billions of stars and planets. It is as though the universe itself carries a common thread, a molecular signature that repeats again and again, binding distant worlds to one another. This idea has profound implications for the question of life beyond Earth. On our planet, water is essential for biology. Every living thing depends on it, from the smallest microbe to the largest whale. If water is widespread throughout the universe, then perhaps life is too. To share water is to share potential. The oceans beneath the ice of Europa may harbor life forms unlike anything we know, yet born of the same chemistry. The clouds of an exoplanet might shelter microorganisms floating in vapor, sharing a distant kinship with us. The universality of water suggests that life may not be a rare accident, but a natural expression of the cosmos, emerging wherever the right conditions exist. Yet even if life exists only on Earth, water still connects us to everything else. The molecules in our blood, in our cells, in the very structure of our bodies are part of this cosmic cycle. We are not separate from the stars, but made from the same elements, carried along by the same molecules, part of the same story. This is what it means to have a shared cosmic heritage. The oceans we sail, the rivers we cross, the rain that nourishes our crops, all of it carries within it the history of the universe. It is a history that belongs not just to Earth, but to every world touched by water. Water also connects us across time. The water we drink today is not new. It has been recycled endlessly through Earth systems, evaporating, condensing, falling as rain, flowing through rivers, and returning to the sea. The same molecules we use today once moved through dinosaurs, through forests that turned into coal, through the veins of ancient fish, and through the soil of the earliest continents. The water on Earth is finite, yet it is infinite in its cycling, a heritage passed from one generation of life to the next. This cycle, bound by gravity and chemistry, echoes the larger cycles of the universe, where stars are born, live, and die, scattering elements to form new generations. In both cases, nothing is truly lost, everything is transformed, everything is connected. To reflect on water in this way is to see that it is not merely a necessity for survival, but a symbol of our unity with the cosmos. Every time we look at a raindrop or a wave, we are looking at something that links us to the stars. We are reminded that our planet is not isolated, but part of a vast and interconnected web of matter and energy. The water that sustains us sustains this truth, that we belong to the universe, and it belongs to us. This recognition changes the way we see ourselves. We often divide existence into categories: human and non-human, earthly and cosmic, living and non-living. But water dissolves those boundaries. It flows through everything, binding the earth to the heavens, the past to the present, and the living to the non-living. It is the common denominator, the molecule that reminds us of our shared origins and our shared destiny. To live on Earth is to inherit this legacy, to carry within us a heritage that is both planetary and universal. In this way, water is not only a physical necessity, but also a profound metaphor. It represents continuity, connection, and heritage. It is the thread that links us to our ancestors and to the stars, to other worlds, and to possible life forms yet undiscovered. When we say that water is a shared cosmic heritage, we are acknowledging that it belongs not to us alone, but to the entire universe. It is the molecule that ties us together, reminding us that no matter how vast space may seem, we are never truly alone, because the same water that flows here flows elsewhere, carrying within it the memory of the cosmos itself. The timelessness of water's journey lies in its paradox. It is both constant and ever-changing. It shifts from vapor to liquid to ice, from raindrop to ocean, from glacier to cloud, yet it is always water. It shapes mountains and deserts, nourishes life and erodes stone, yet it remains the same molecule, unbroken, enduring. It belongs to no single moment, no single place, no single generation. It belongs to all time, to all worlds, to all of existence. Water is more than a substance flowing through rivers, falling as rain, or stretching endlessly across our oceans. It is the ancient bond between Earth and the cosmos, a traveler older than our planet itself. From the birth of hydrogen in the Big Bang to the forging of oxygen in the hearts of dying stars, water carries within it the memory of creation. It drifts through interstellar clouds, freezes onto comets, hides beneath icy moons, and flows across alien worlds. On Earth, it gathered into oceans that became the cradle of life, a solvent where chemistry blossomed into biology. Every sip of water connects us to this cosmic story. The molecules in our bodies once drifted in the cold depths of space, long before the sun lit our skies. The same water that nourishes us today may have once passed through ancient forests, swirled in the seas of early Earth, or even lain frozen in comets at the edge of the solar system. This continuity makes water not only a necessity of life, but also a symbol of unity, reminding us that we are part of a shared heritage that spans stars, planets, and time itself. To reflect on water's journey is to see ourselves differently, not as isolated beings on a single planet, but as participants in a story written into the very molecules of the universe. Water connects us to our past, sustains our present, and points toward our future, whether here on Earth or across the cosmos. It is the quiet witness to creation, the cradle of life, and the timeless traveler that carries with it the essence of continuity, connection, and eternity.